So, chemists use it a lot. Kind of fun, I guess. So, y equals a times 1/2 to the x over n. Hi, my dog just showed up. Go away, Ginger. To the x over n. So, after that, you can plug in some numbers into your equation if you have a problem. Ginger, go away. Suppose a half-life of a certain substance is 20 days and there are 500 grams present initially. Write the equation. So, you know the half-life is 20 days, so your n value is going to be 20. So, that's pretty easy. 500 grams initially, that's obviously your a value. So you can write out an equation. Y equals 500 times 1/2 to the x over 20. So, then it gives you some more stuff to plug in. How many grams will be left after 200 days? So, you know that your x time is going to be 200, and 200 over 20 is 10, obviously. So, your equation will be y equals 500 times 1/2 to the 10. Ginger, go, shoot. So, that's your equation. It's nice and easy. It's pretty much just another application. So, you solve that out, and you get 0.488 grams. Nice and simple. So, you can do a lot of stuff with this. Pretty simple. But there's one more application to talk about, which is population. Population, it's basically the same thing, except you have to think about growth rates in terms of like a different way of thinking about growth rate. So, it's the same equation, y equals a times b to the x over n. So, a certain city has a population of 86,000 residents. If the population grows at a rate of 4% each year, what will the population be in 10 years? So, to solve this, we are going to write out our equation. So, y equals our base value is 86,000 residents. 86,000. And our b value. So it grows at a rate of 4% each year. So if you think about that, you can't just put 0.04 for the rate, because that'll make it go down, obviously. So to make the growth rate of 4%, you have to put 1.04 for the growth rate to the 10th power, because it's 10 years and you don't have a time for your n value. So that's an easy equation. Then, I mean, that's basically all you have to do. You just plug it in and you get 127,301. So, I mean, it's just another application of this equation. So that's all I have for you, and my dog's being really annoying. So, bye.
Now we're going to be learning about exponential decay. Exponential decay is pretty much the same as exponential growth was, except this time, obviously, your number is getting less instead of more. In fact, the equation is pretty much exactly the same. It's y equals a b to the x over n, just like it was for exponential growth. Where y is your current amount, a is your initial amount, b is the factor of growth or decay, x is the length of time, and n is the interval of time, therefore making x over n the number of time periods. The only big major difference is that this time b is always less than 1. And you can't forget that, because otherwise it's not decay. For example, we're going to take a hypothetical situation of a population of 100 people that decreases by 20% every 5 years. And we're going to look and see how much it would be after 10 years. So, to put in the growth factor, you don't just put the 0.2, the 20% that it gives you. That would be wrong. That would decrease it by 80%, not 20. To decrease by 20%, you would have to take 1 minus the 0.2 that it provides for you. And therefore, you get a decay factor of 0.8. So working from that, you can go ahead and change 10 over 5 to 2. Fairly obvious. And then you can square your factor here. Becomes 0.64. And then obviously, calculations are very easy in this example, though I'm sure they'll be much harder in anything we do in class. You're left with a population of 64 people. Yay, 64. Now, you can use the original equation that you got to work it to find any number in that equation, whether it be x or n or b or whatever, whichever variable you want to find. I'd also like to look at another example, which is that